the first two lectures of this module, we discussed some special mechanisms, namely approximate state line mechanism and exact state line mechanisms. In today's lecture, we will discuss another special mechanisms which are used for steering the automobiles and are called steering mechanisms. As we know, when an automobile wants to take a turn, the front two wheels have to rotate about the vertical axis. Let us say this is the front view of the one of the wheels, front wheels. Front wheel, front view. As we see, the front wheel is normally mounted on a short axle. This is a short axle which is pivoted to the chassis, and the pivot axis can be vertical. This is the body of the automobile, and this is the pivot axis. When the car wants to take a turn, it is this front wheel rotates about this pivot axis. There are other types of steering mechanisms where this pivot axis may not be vertical. It is inclined from the vertical. Again, this is the front view of one of the front wheels. This is the road surface. This is the short axle about which the front wheel can rotate, and during the steering action, when the car wants to take a turn, this wheel will rotate about this pivot axis, and this is the body or chassis of the automobile. What we see in this arrangement, while taking a turn, the body of the automobile is lifted. Consequently, when the hand wheel, steering wheel is released, the car automatically comes to its original position and the wheel becomes straight. We shall discuss this type of steering mechanism in our subsequent discussion. First, we should discuss what is the steering requirement. When the automobile takes a turn, either a right hand turn or a left hand turn, it is imperative that all the wheels, that is the two front wheels and the two back wheels, continue to roll. What is the rolling condition? That at the contact point, velocity must be 0. It is easy to see that if I consider this contact point, say C, and it is the center of the wheel if I call O, we know velocity of C is velocity of the center of the wheel O plus omega of the wheel cross AC. Now, for Vc to be 0, it is this vector must cancel this vector. That means these two vectors must lie in the one plane. Now, omega cross OC lies in the plane of the wheel. So, the VO must lie in the plane of the wheel. This is the basic steering requirement, that the velocity of the center of the wheel must lie in the plane of the wheel, such that when the wheel rotates, the contact point velocity can be 0, that is, the perfect rolling condition can be maintained. Steering requirement is rolling condition must be maintained. I hope this is clear, that when the car takes a turn, the velocity of the center of the wheel, if it does not lie in the plane of the wheel, then there will be velocity of this contact point, because this lie in the plane of the wheel. Omega is this way, OC is this way, so omega cross AC is in this direction, that is in the plane of the wheel. So, VO must lie in the plane of the wheel such that VC can be 0, which is required for perfect rolling condition. So, the wheels, the front wheels must turn appropriately such that the center velocity must lie in the plane of the wheel. To maintain this steering requirement, let us see what is the condition needed. Let us now see the condition that requires to be satisfied such that the steering requirement is obtained. The steering requirement is fulfilled. Let us consider the two back wheels. These are the rear wheels. As we know, the two rear wheels are connected to the differential, which is fixed to the body of the automobile. This differential allows the two rear wheels to rotate at different speeds when the car is taking a turn. For example, if the car is taking a turn like this, then this becomes the outer wheel and this becomes the inner wheel, and we need that the outer wheel should rotate faster as compared to the inner wheel. This differential speed can be created by this differential, as we shall discuss later on when we discuss gearbox. The distance between these two wheels is called wheel track. Let us say wheel track is A. This is the top view of the car, and the distance between the rear axle and the front axles, this distance let me call B, which is called the wheel base. Similarly, there is another front wheel. So these are the two rear wheels, these are the two front wheels. As we see, the front wheel axles are mounted on these pivots on the body of the automobile. Now, when the car takes a turn in this direction, these two front wheels must rotate. Let us say this axle rotates about this pivot and this axle rotates about this pivot. These two rotations must be such that all these axles must intersect at one point. The rear axle and the two front axles, while the car is taking a turn, must intersect at one point. Let me call it I. That is, this I is the instantaneous axis of rotation for the entire car body as a rigid body. So this is instantaneous axis of rotation for the car body. As we see, in this situation, the wheels, which is now rotated like this, the velocity of the center of the wheel is in this direction, that is contained in the plane of the wheel, and this wheel which is rotated like this, the wheel velocity of the center of the wheel is perpendicular to this line and again contained in the plane of the wheel, which is the requirement for perfect steering. These two wheels must rotate. Say this is phi and this angle is psi. So for perfect steering, this phi and psi should be such that these two front axles and the rear axle passes through one point. This is the steering requirement. So let me find out what is the condition. Let us see. If we say that the distance between these two pivots in this direction is p, and if I say the distance of this instantaneous axis of rotation from this pivot is say x. So what we see that this distance is the wheelbase, which I called B. So what we can write that cot phi is x over b. Cot phi is x over b. Similarly, cot psi is x plus p divided by b. So if I subtract, we are getting cot psi minus cot phi is P by B. So, for perfect steering requirement, the rotation of the two front wheels, the inner wheel by phi, which has to rotate more, and the outer wheel by psi, which has to rotate less, this phi and psi should be related by this equation: cot psi minus cot phi is P by B, where P is the distance between the two pivots onto which these two front short axles are mounted, and B is the wheelbase. Now, we will see how we can achieve this condition by using different types of steering mechanisms. Now that we have obtained the steering requirement, that is the condition that must be fulfilled by the steering mechanism, let us discuss a particular steering mechanism known as Davis steering gear. In this Davis steering mechanism, we use a 6-link mechanism with 7 lower pairs. Let me first draw the mechanism. This is the Davis steering mechanism. As we see, these are the two front wheels mounted on short axles, and the axles are pivoted on the body of the automobile. Let us consider that the car is taking a turn in this direction. So, as we see, let me call this point O2, this point A, this point B, and this point O6. This is a 6-link mechanism. Link number 1 refers to the body of the automobile. This is link number 2, and this block in which this link number 2 can slide, this is link number 3. Link number 3 is hinged to this link, which is link number 4. And this block, which is hinged to link number 4 at B, is link number 5, and this is link number 6, which is nothing but the axle of this outer wheel. Similarly, link number 2 is nothing but the axle of the inner wheel. These are the axles which can slide in this link this is another axle which can slide in this link, and these two links are connected by link number 4 through revolute pairs. So overall we get a 6-link mechanism. 1, 2 is the axle of the inner link, 3 is this block in which this link 2 can slide, link 4 is this rod, this link, which can slide in the body of the automobile parallel to the direction of O206. Link 4 is in sliding motion with respect to link number 1, that is body of the automobile. There is a prismatic pair here. Link number 4 has a revolute pair with link number 5, and link number 5 has a prismatic pair in this direction with link number 6, which is nothing but the axle of this outer wheel. Obviously, the mechanism has to be symmetric such that similar turn can take place either in this direction or in this direction. The car can turn in this way or the car can turn that way. Now, as we see, this mechanism is symmetric. That means this angle is same as this angle. Now, our only requirement is to find the value of alpha such that the steering requirement is satisfied. Let us say the rotation of this link 2, how it is steered? It is this rod is moved in this direction. That means suppose the A comes to this point, we call A prime, and B comes to exactly by the same distance here, let me call this point B prime. This rod AB moves horizontally parallel to O206 from AB to A prime B prime. Consequently, this link 2 rotates by theta 2, and if I join O6 with B prime, link 6 has rotated by this angle, which is theta 6. That is, this angle is theta 6. So, theta 2 is the rotation of this axle, theta 6 is the rotation of this axle, as AB goes from AB to A prime B prime. You have to find the value of alpha such that the steering requirement is fulfilled. If we remember, this distance between the pivots we denoted by P, and the steering requirement was cot of theta 6 minus cot of theta 2 was P by B. In our previous diagram, theta 6 we denoted as the rotation of the outer wheel, which was psi, and theta 2 was the rotation of the inner wheel, which we denoted by phi. And we said cot psi minus cot phi should be P by B, where P is the distance between the pivots and B is the wheel base. Let us say in the state configuration, these two lines meet here, and in this rotated configuration these two lines meet there. We call this point R and this point S. Extension of link 2 and extension of link 6. In the state configuration, when the wheel was straight, meet at R. When the wheel turns, they meet at S. It will be very easy to show that this line RS, let me use a different color, that this line RS is parallel to O2O6. We can easily prove that RS is parallel to O2O6. To prove that, we have to remember that this link length 4 between the two revolute pairs is same, that is A prime B prime is same as AB. B prime is same as A prime, and AB, that is the length of this rigid link 4, is A prime B prime. And we already started that this prismatic pair was parallel to O2O6, that is AB is parallel to O2O6. So what we can write, that RA by O2R is same as RB by O6R is AB by O2O6, because this line is parallel to this. So these two triangles are similar triangles. RAB and RO2O6 are similar triangles, because AB is parallel to O2O6. So you can write RA by O2R is same as RB by O6R is AB by O2O6. Now, A prime B prime is again parallel to O2O6. So for these two triangles, S A prime B prime and S O2O6, we can write similar relationships, that is S A prime divided by O2S is S B prime by O6S is A prime B prime by O2O6. These two white triangles are similar, and these triangle and this blue triangle are similar, because this line is parallel to this line. Now, AB is same as A prime B prime. AB is same as E prime B prime. So these are also same. So we can write RA by O2R is same as RA by O2R is same as SA prime by O2S. RA by O2R is AB by O2O6, and SA prime by O2S is A prime B prime by O2O6. AB is same as A prime B prime, so this is equal to this. Now, if RA by O2R is same as SA prime by O2S, then I can say this line A prime is parallel to RS, which means RS is also parallel to O2O6. So we have just proved that this line RS is parallel to O2O6. To determine the required value of alpha such that this tearing condition is fulfilled, let us note that because RS is parallel to O2O6, this angle is also alpha. Similarly, this angle is also alpha. Now, this is the angle theta 6. This is the angle alpha. So, this angle is alpha minus theta 6. This angle is alpha, this angle is theta 2. So, this angle is pi minus alpha plus theta 2. Now, we use the triangle sine law for this triangle, namely O6RS. We can write RS by sine of this angle, which is theta 6, RS by sine of theta 6 is same as O6R divided by sine of this angle, which is alpha minus theta 6. So, this is O6R sine of alpha minus theta 6. This angle is alpha, this angle is theta 6. So, this angle is alpha minus theta 6. Now, in this triangle, we apply the sine law. RS by sine of theta 6 is O6R divided by sine of this angle, which is alpha minus theta 6. Again, we apply the triangle sine law for O2RS, this triangle. So, O2R divided by sine of this angle, which is this. So, O2R by sine of pi minus alpha plus theta 2 is same as alpha plus theta 2, is same as RS divided by sine of this angle, which is theta 2. So, we apply the sine law for the triangle O6RS and O2RS to get these two relationships. Now, from here, if I divide this equation by this equation, we get sine theta 2 divided by sine theta 6 is same as sine alpha plus theta 2 divided by sine alpha minus theta 6. We just divide this equation by this and this equation by this to get this relation. If we expand, we get sine theta 2 sine alpha cos theta 6 minus sine theta 2 cos alpha sine theta 6 is same as sine theta 6 sine alpha cos theta 2 plus sine theta 6 cos alpha sine theta 2. Just cross multiplying this with this with this, we get this relation. Now, we can divide all these 4 terms by sine theta 2 sine alpha sine theta 6. So, that I get cot of theta 6 sine theta 2 sine alpha cancels, divided by sine theta 6 I get cot. Again, from here I get minus cot alpha. This sine cancels and this gives me cot alpha. Here I get equal to cot theta 2 and here I get plus cot alpha. So, that gives me cot theta 6 minus cot theta 2 is 2 cot alpha. And for perfect steering condition to be maintained, I know cot theta 6 minus cot theta 2 should be P by B, where P is this distance O2 O6 between these two pivots and B is the wheelbase. So, this is equal to P by B. So, alpha is half of cot inverse P by V. So, let me explain this Davis steering gear once more. This is a 6-link mechanism, where link 1 refers to the body or chassis of the automobile. Link 2 is the inner wheel axle. We considered a turn like this. So, this front wheel becomes the inner wheel, and link 6 is the short axle of the outer wheel, that is link number 6. Link 3 has a prismatic pair between 2 and 3, and link 5 and 6 has a prismatic pair between them, and link 4 has 2 revolute pair at its end and a prismatic pair with link 1, and the direction of this prismatic pair is parallel to O2, O6. The mechanism is symmetric because we have to take identical left turn and right turn. Only design parameter is to find out this angle alpha, and we found out that alpha should be half cot inverse P by B, where P is the distance O2, O6 and B is the wheelbase. Then this steering action will be maintained. So, this is a 6-link mechanism where we have R, then a P pair, then again an R pair, then again a P pair, then again an R pair, then again a P pair and an R pair. So, it has 7 lower pairs alternately RP, 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 R. Though this Davis steering gear can maintain the perfect steering condition for all radius of turning, it is cumbersome to make because there are so many prismatic pairs and it is difficult to maintain. So, Davis steering gear is a 6-link mechanism with 1, 2, 3 prismatic pairs and 4 revolute pairs. And due to the difficulty of this prismatic pair, it is decided to forego this advantage of maintaining the steering condition for all the turning radius. We can go for a simpler mechanism which will maintain the steering condition for certain values of the turning radius and will not be exactly satisfied for all other turning radius, and there will be a little tendency of slide slip or the transverse motion of the wheels at the point of contact. Let me now summarize what we have covered today. We started discussion on steering mechanisms which are used in automobiles. The front wheels of the automobiles are mounted on short axles which are pivoted to the body of the automobile. For perfect steering condition, that is the wheel continue to roll even when the car is taking a turn, we need that the velocity of the wheel center must lie in the plane of the wheel, so that the contact point of the wheel has 0 velocity, maintaining pure rolling. This requires that the 2 front wheels must be rotated by different angles depending on the turning radius. The condition we obtained was in terms of the distance between the pivots of these 2 short axles and the wheel base, and we showed that a 6-link mechanism using alternately R and P pairs, 7 of these, 4 R and 3 P pairs, which we call Davis steering gear, can maintain this perfect steering condition for all turning radius. But there is difficulty of this complicated mechanism both for manufacturing, it is costly, and also for maintenance because of 3 prismatic pairs.